For a translational polygonal robot, what we are going to do is we need to compute the free space based on this polygonal robot. And this, in order to compute free space, you remember the free space was the difference of this bounding box from the polygons in the configuration space. So it was from the C obstacle. So we had this term C obstacle, which was a mapping, the configuration space obstacle, which was a mapping of a workspace polygon to the configuration space. In the point robot, these two polygons were the same. So C obstacle was equal to the polygon itself, or CP was equal to P. So this is denoted by CP as well, was equal to P when in the case of a point robot. But in polygonal robots, what we are going to have is that the C free space, what we want to find is that the CP is defined as, it cannot be P anymore. It's going to be this obstacle are going to be the set of points, set of all xy, in which our robot's configuration it's mapping to the this configuration space mapping to the workspace is in the intersection is not equal to empty set. Okay, so if your robot, so actually just as you said, our xy is actually a mapping from the configuration space to the workspace. So it's the reverse of here. The P to CP was a mapping from workspace to configuration space for obstacles. And this RXY, since XY was a point here, this single point is converted to the robot, the polygonal robot in the workspace. So if this configuration makes the robot in the workspace intersect with a polygon, with this polygon, obstacle polygon, so if there is an intersection, then this xy is an obstacle, is a forbidden configuration in the configuration space. Okay, so all such sets of points, all xy in which the robot intersects with that polygon is going to be the configuration space obstacle corresponding to that polygon. And what we need to do is, if we compute this configuration space polygons, again, we would just take their union and take the difference from the bounding box. Okay, if we find these configuration space obstacles. Now, how do we compute this is the next thing we are going to see. So how do we compute all the xy points in which this configuration is going to intersect with this P? The solution I'm going to describe is based on Minkowski sums. And first let me define what a Minkowski sum is. A Minkowski sum of two polygons, not necessarily convex, is given by P plus Q, in which P is element of the first polygon and Q is the element of second polygon. Okay, so all points that belong to first polygon, and if you take all, it's like a Cartesian product. It's actually it's like a Cartesian product. So you take all points that belong to S1 and you take all points that belong to S2, you add them up as vector addition. Okay, so if P is equal to Px Py and Q is equal to Qx Qy, P plus Q is equal to Px plus Qx Py plus Qy. Okay, so the addition is defined as vector addition, and it's defined like this. So all the points, so we add all the points, all the points that belongs to these individual polygons to get the Minkowski sum. So this is the Minkowski sum of two polygons. Now, What I'm going to show next is really interesting first, but we are going to prove that it is true. We are going to see that CP is equal to the polygon Minkowski summed with minus R00. Okay, so it's not the Minkowski sum with R, the robot itself, but a reflection. So, and also in order to, first of all, in order to be correct and complete, we need to also define what this minus means. We haven't seen this minus mapping yet. Okay, we have just seen R, X, Y. We just defined R to be a transformation here, and minus R is defined as a reflection. So it's here's the complete description of minus R. So it's like this. It's just we take. Okay. So for a point P, we define, for a point P, Px, Py, we define minus P to be minus Px minus Py. Okay, so it's the reflection with respect to origin. And for a set, if we have a set, this R is going to be a set of points in the workspace. So for a set, what we have is, it's minus P. P is element of S. Okay, so to complete these definitions, what we have is, this is, you can apply this to R. So if you take the Minkowski sum of the reflection of your polygon in its original position at R00, if you take the Minkowski sum of this with the obstacle, what you get is as an obstacle in the configuration space. So after you find this for all the polygons you have, the next thing is to take their union and take their difference from the bounding box, and we can use the same trapezoidal map technique to find the path. Now let's prove this. Is it really true? Okay, so is it in order to prove it, what we need to show is that okay, so here we are tying these two things. Okay, so here was the original definition of CP. So the configuration space obstacle are all the points in which this RXY and P is intersects. Okay, so in order to prove this, we need to show that this is true if and only if this is true. Okay, so we need to show it both ways. So first, given these two, they don't intersect, so we need to prove the both sides of the claims. Okay, so first suppose that these two intersect. Okay, now first we are going to suppose that this is true, and we are going to show that this equals to this, and then we are going to assume that this is true, and we are going to see that they intersect. Okay, if RXY intersects P, it means that there is a point Q, which is QX, QY. Let this point QX, QY be a point in the intersection. Okay, so if they intersect, there exists a point within the intersection. Okay, so it means that this Q is an element of R, X, Y, and also Q is element of P, right? I mean, this is what intersection means. It's an element of both R, X, Y, and this polygon P. So if Q is element of R, X, Y, then we have Q minus X, sorry, QX minus X and QY minus I should be an element of R00, right? I mean, if QXY is a point when you translate the robot XY, if you undo this translation by minus X and minus Y, this new point should be an element of the robot in its original configuration. Okay, so we have this, and we can also write this. Okay, if we have this, we can write it like this. If this is an element of this, if we just take the minus of this R00, it means that minus qx plus x and minus qy plus y is an element of this reflection. Okay, so if you reflect the point, so this is a point which is a member of this original configuration. So if you take the reflection of this point, it should be a member of the reflection of this polygon. Okay, so it's a member of this polygon. We also have q is equal to p, so qx qy is an element of pb. We know that without our first assumption. So this implies that xy, the point xy, is going to be element of, I mean, if you, now we know that this is an element of P, this is an element of P. Now apply Minkowski sums on this. So what is the Minkowski sum of P plus minus R00? What we need to do is Qx plus this, which is Qx minus Qx plus X, which gives you X, and Qi minus Qy plus Y, which gives you Y, which means that Xy is an element of R minus R00, Minkowski sum P. Okay, so we show that if they intersect, there's a point, this xy is also belongs to their Minkowski sum, is an element of their Minkowski sum. And the other part of the proof is also really simple. We now first assume that this is true, and assuming that this is true, what we do is this. Okay. If there's an xy, which is part of CP, and an element of this, now we assume that this part is true, then we need to show that there must be this xy should also be at their intersection, at the intersection of these two. Okay? Now, if xy is an element of this Minkowski sum, then it means that there's a point Rx, Ry, which is an element of R00, and there's a Qx, Qy, which is an element of P, such that this xy, because of the definition of the Minkowski sum, okay, I mean, if this, just take an arbitrary point here, Rxy, which belongs to this R00, and take an arbitrary point which belongs to this P. Based on the Minkowski sum definition, what you know is that this xy is equal to this is, let's have them qx, qy, it doesn't matter. Then we are going to have qx minus rx, qy minus ry. So this comes from the definition of Minkowski sums. Okay? In other words, if we look at this, qx is equal to rx plus x, okay, and qy is equal to ry plus y. Okay, and this equality means that qx, if you add rx and ry to both of these points, if you translate both of these points plus rx amount, x plus rx is going to be qx, and qy is going to be ry plus y, which means that if you translate your robot, which was this rxiy, what was that? Rxiy was a point in the robot. Okay, if you translate this point, x and y amounts, what do you get? A point in the polygon. It means that this translation intersects the robot with the polygon. So now you start from the Minkowski sum, you find that this point is an intersection point. Okay, so here, so this concludes the proof, which shows that in order to find the C obstacle, all we need to do is compute the Minkowski sums of a polygon with the reflection of the robot with respect to origin. Now, the next, what I'm going to do is talk a little bit about Minkowski sum. They have really interesting properties, Minkowski sums. One of these properties is that the Minkowski sum of a convex polygon with another polygon, they cannot be really arbitrary polygons. But they're very interesting properties that they are like disks and squares in such a case. There's a notion called pseudo disk. Okay, a pseudo disk is a pseudo disks. Sorry, a pair of pseudo disks. If you have two polygons, okay, and if these two polygons can intersect at most at 2 points, we call them pseudo disks. So, for example, if you have circles, okay, if you have circles, and they can be any arbitrary size, okay, and if these two circles, if you may ignore the inclusion of one circle in another, when you intersect two circles, the number of intersection points can be at most 2. Okay, a circle cannot intersect with another circle at 4 points, but two ellipses can. Okay, if you have two ellipses, for example, they can intersect at most 4 points. But if you take two circles, this is impossible. Okay, they're always going to intersect. If you take two circles, they can intersect at 2 points. Another definition of this pseudo disks is that actually the intersection of this boundary with the interior of the other polygon is if it's a connected region. Here in ellipses it's a disconnected region. So the intersection of this boundary, intersection of this interior of this polygon with the other polygon, I mean not the intersection, I mean this difference is disconnected. But if you do it in circles, it's always going to be connected. If you intersect two circles, the intersection of the boundary with the other circles is always going to be a connected region. So, and this is not only a property of circles. If you take squares, okay, squares also are pseudo disks. Okay, this is really interesting. I mean, polygons, they don't need to be circles. If you take any number of squares on the plane, with different sizes, squares are always going to be pseudo disks. Their intersection is going to be a connected region. At most, it can be at most 2 points. Now, what is interesting is that the Minkowski sums are also pseudo disks. Okay, the original polygons may be arbitrary polygons. For example, take 3 arbitrary polygons, P, Q, R. Okay, this is the theorem. If take 2 convex polygons, this is theorem 13.8 in the book. I'm just going to mention that I'm not going to go into too much detail about pseudo disks, okay? Because we are not going to use this property in our algorithm at all. I mean, so it's just saying that Minkowski sums are not only used for finding in robot motion planning. It's studied a lot in other contexts as well, and they have different properties. This pseudo-disk property is one of them. If we take 2 convex polygons with disjoint interiors, separate 2 polygons, and take another convex polygon, if we take the Minkowski sum of this third polygon with the 2 separately, these resulting Minkowski sums are pseudo-disks. Okay, so this is an interesting property. I mean, the convex polygons are not pseudo-disk in general. For example, take 3 rectangles. Okay, take 3 rectangles, long rectangles, 3 long rectangles, all of them are convex, and none of them, these rectangles, originally, they are not pseudo-disk pairs. There is no pair of, rectangles may intersect with each other in 4 different points. So a rectangle, a long rectangle, is not a pseudo-disk with another long rectangle. But if you take the Minkowski sum of these rectangles pairwise, take the Minkowski sum of the 2 long rectangles and the other 2 long rectangles, the resulting 2 polygons are pseudo-disks. So this is an interesting property of Minkowski sums. And here, in order to compute the Minkowski sum, we are going to make use of an observation which is relating extreme points of the polygons. So given 2 convex polygons, okay, these are separate 2 convex polygons, and given a direction, for example, direction this. And the extreme points in this direction in both of these polygons, the summation of these vertices gives us a vertex of the Minkowski sum in that direction. So let me reword it correctly, this observation. Let's see, it is, yeah. No, it's not this one. It's 13.4. Yeah. An extreme point in this direction is the sum of extreme points. So if we want to find out what is the, if this is the Minkowski sum, okay? What is an extreme point of this Minkowski sum? So if I don't know what the Minkowski sum is, okay? It's unknown to me right now, but you want to find out what is the vertex of this Minkowski. So you want to find in order to compute this Minkowski sum, you need to find its vertices. Okay, so it's another polygon. It's going to be another polygon. So what it says is that if you take the same direction D, the extreme point in this direction is equal to the extreme points in this direction of these individual polygons. So if you know that the extreme point of this polygon P is this point P, and this extreme point of this polygon R is R in this polygon, we know that in direction T, the vertex of Minkowski sum is going to be P plus R. Okay, so this is an interesting observation, and it is going to help us to drive an algorithm to compute Minkowski sum. So since the vertices of Minkowski sums are extreme points in some direction, and these are convex. So these are 2 convex polygons, and the resulting Minkowski sum is also going to be a convex polygon. Okay? So they are convex, and the extreme points, what does this remind you? Convex halves. Okay? So what we can do is we can take every pair of vertices. For example, if this has m vertices and this has n vertices, we may take the sum of every pair of vertices. So P1 plus, so Pi plus Pj. So for all ij, okay, so for all ij, we may compute this point. Okay, so this is going to give us m times n points, summations, but not all of them. Actually, all these points should be inside the Minkowski sum by definition, right? Because any point, not only the vertices, you just take any point here, any 2 points that are inside the polygon, their summation is a member of the Minkowski sum. So all these points, so it's like really a Cartesian product. So what you have is, so all these points are going to be in all these possible pairs of points are going to be in the Minkowski sum. But the question is, which are extreme points? And the convex hull algorithm gives you that. Okay, if you compute the convex hull of all these m times m points, the resulting convex hull is going to be the Minkowski sum. Okay, so this is, you can find the Minkowski sum in OMN time. Now, I'm going to write an algorithm, a pseudocode of an algorithm, which reduces this to OM plus n. So from quadratic complexity to linear complexity. So we can reduce this to n. And it is based on, I think it's, the book does not mention this, but it looks very much like, I mean, it's a gram-scan algorithm. I mean, it looks like, I mean, here, what we don't make use of, the fact is that these convex polygons, we are given two convex polygons. These are, their points are not just arbitrary. We are given an ordered set of points. Okay? And this algorithm does not make use of this fact. It just takes all these points as random arbitrary point clouds. It takes pair of all these points and then computes the convex hull. But what I know is that what the convex hull in the convex hull algorithm, for example, in gram-scan algorithm, what you need to do is you need to sort these points. But the points are already sorted if you are these two polygons that are given to us, they are already given to us in some order. Okay? If you are given a polygon, its vertices have to be given in some ordered manner to you, otherwise the polygon is not defined. So we can make use of this fact to reduce it to linear complexity, and this is what we are going to do. The algorithm proceeds like this. First of all, it starts with an extreme, a pair of extreme points that you know. Okay? For example, what you can take is that in both polygons, take their lower points, the lowermost points. Look at their y coordinates, and you can do this in linear time in both polygons. And this tells you that actually these are 2 points which are extreme in minus y direction. Okay, so the lowest y coordinate vertices are 2 extreme points that are extreme in minus y direction. So what it tells you is that the addition of these 2 lowermost vertices is a vertex in the Minkowski sum. Okay, so you first start adding, you immediately know that, you know these 2 points are in the Minkowski sum. Now, what you do next is, by looking at the angle, the edges, you look at the edges of, you compare, let me just draw it on the board. And let's try to do it on these polygons, for example. So these are first, let me just name this V0, for example. And this is W0, the lowermost coordinates. And this is V1, V2, V3, and W1, W2, W3. Now, what we do is, we check the angle this edge and this edge makes with the positive x-axis, just like gram-scan. Okay? So whichever is smaller is going to tell us that this one and this are also going to be, I mean, we are just going to rotate these lines, but one by one, whichever comes, we are just comparing these 2 angles actually, the alpha and theta, okay? If alpha is smaller than, if whichever is greater, no, actually we take the smaller one here. This is what I said first was true. If this angle, if alpha is smaller than theta, what we do is we move to this next vertex, here V1, and we add V1 and W0 again to our Minkowski sum. And we continue doing this, then we compare this angle, which makes with the x-axis, with this angle. Now theta is going to, this is going to be alpha now, theta is going to be smaller, and then we are going to proceed to the next vertex here. So we are going to either increment, we are going to either go to the next vertex in this polygon or in this polygon, and if these two angles are equal to each other, we are going to go to the next vertices in both of these polygons at the same time. And when we go to the next vertex, so at this next step, V1 plus W0 is going to be a vertex of the Minkowski sum. And if we increment the other one, for example, in the next step, we are going to increment W1, and W1 and V1 plus W1 is also going to be a member of this Minkowski sum. And what this also shows you is that at the end, you're either incrementing one or the other. The number of vertices of the Minkowski sum, so what is the complexity of the Minkowski sum? Let's try to think about it next. It can have at most m plus m vertices. Okay, so we either increment, if we increment all of them at the same time, we are going to have the maximum, I mean, if they have equal number of, we can increment all of them at the same time if they have equal number of vertices. If both of them have m vertices, and if all the angles are equal, it means that if we have the same copy of the same polygon, the Minkowski sum is going to again have m vertices. But it's going to, yeah, that's an interesting question. If you have two of the exact copy of the same polygons, what is the Minkowski sum of these two? Is it like a doubled version of the triangle? Not double, but it's still going to have three vertices, right? Because the extreme points in extreme directions are going to be unique. Based on this algorithm I described, we are going to increment both vertices at the same time. So it's going to be, it's whatever, if these are V0, V1, V2, and W0, W1, W2, the Minkowski sum is going to have vertices which are these. Okay, so these are, the Minkowski sum is going to have three vertices. However, if the polygons are different, they can be different convex polygons, and we can either increment one of them and the other. If we continue incrementing these two one by one separately, at the end we are going to have m plus m vertices. So the Minkowski sum may have m plus m vertices. So the number of vertices are increased, okay, if in two convex polygons. So this is how we are going to compute the Minkowski sum. It's very simple to implement algorithm. Okay, just doing an angle check and just go to the next vertex, add that vertex to the Minkowski sum. So the algorithm is very simple to implement. And if we have two convex polygons, we know that the Minkowski sum is at most have this complexity, this many vertices. Now, let's get back to our original problem, in which the polygons are not necessarily convex polygons. Okay? If we don't have convex polygons, what we do? Again, we use an existing known algorithm. We triangulate them. We know how to triangulate polygons. So we can triangulate them, and we can have ourselves a concave polygon composed into the triangles which are convex. So, and now, but there's a complication here, which is the Minkowski sum of a convex polygon and a concave polygon is not going to have n plus m vertices. The complexity increases like this. The number of edges, or the number of vertices of the Minkowski sum of two convex polygons is n plus 1, n plus m. The Minkowski sum of a convex polygon with a non-convex one is n times m. That's the at most, that may have at most this many vertices. And there's a worst case example in the book which actually has this complexity. Again, it looks something like this. This is the non-convex polygon, and if you add a certain convex polygon to this, you are going to add this to all of these patches, which is going to give you n times m complexity. And if you have two non-convex polygons, their Minkowski sum has at most this many vertices, so n square m square. Well, this is what we do to solve the translational robot motion planning problem. We compute the configuration obstacles, C obstacles, by computing the Minkowski sum of each polygon with the reflection of the robot around the origin. And then we get ourselves a list of CPs, okay, the forbidden spaces, but it's not the union of these polygons is the forbidden space. But taking the union of them was easy. Since these polygons were disjoint, if you remember the point-like robot, we had obstacles which are disjoint polygons. Now, the thing with Minkowski sum is that after you enlarge these polygons, the original polygons, in the configuration space, your polygons may not be disjoint. So in the configuration space, C obstacles may overlap. When does this happen? If your robot intersects with two workspace polygons at the same time. Okay, for example, if there's a polygon like this here, another polygon like this here, and your robot intersects them at the same time. What does this mean? The Minkowski sum intersects. So these obstacles in the configuration space, when they are enlarged, they intersect. So taking the union is not that easy. I mean, we cannot use trapezoidal map directly on these polygons which have intersecting edges. Okay, we don't have, the intersection points are not defined, so we don't have a valid doubly connected edge list here. So what we need to do is we need to compute the intersection. The union. We are not interested in the intersection. We need to compute the union of these obstacle vertices, and we can do it recursively by divide and conquer approach. For example, first we find the we find the union of half of the obstacles, and we find the union of the other half of the obstacles, and at the end we can compute the union of these two final results. And computing the union, so each of the recurrence relation becomes like this: Tn is equal to Tn over 2 plus Tn over 2 plus the union of two convex regions. And taking the union, we know that it can be done in n log n time. So it's Tn over 2 plus Tn over 2 plus n log n gives us an n log square n algorithm. Okay, so we have n log n algorithm to compute the forbidden space. So this first computes the forbidden. The union of these CPs gives us the forbidden space, and the difference of this forbidden space from the bounding box is going to give us the free space. After you have the free space, now even though your robot is not point-like, since you are working in the configuration space, that's the good thing about the distinction between configuration space and workspace. After you compute this Minkowski sum, you find your path as if your robot is like a point. Okay, since you enlarge the polygons, now you can treat, because in your configuration space, your translations are points, x, y. So you don't need to deal with what is the shape of your polygon robot anymore. You can apply the exact same algorithm, the trapezoidal map and road map algorithm, to this new free space that we compute by using the Minkowski sums. Okay, so this is how we solve the translational polygonal robot problem. And what can we do for the rotational case? Now let's discuss the rotational case. And I'm not going to go into details of the rotational robots, but here I'm going to give you some hints about what kind of a roadmap we can compute. Here our configuration space is really not two-dimensional anymore. In a rotational robot, we have x, y's, and we have thetas. And for a point-like robot, this is not a point-like robot is not rotational, or even a circular robot. It doesn't need to be point-like. It may be a circular. Again, rotation is not considered in a circular robot. So what we know is that we have a polygonal robot, which is not like a circle or a point. So now the thing is, as the robot rotates, how does the CPs look like? Okay, for example, in a certain rotation, we compute the Minkowski sum. But if you rotate the robot slightly this way, what will the configuration, how it will change in the configuration space? So our configuration space should be a union of, but it shouldn't be a union because, to be absolutely sure you never intersect it, you may take the union of all these rotations and still get yourself a 2D dimensional configuration space. But what happens is that, let me show you this. If you do that, you may never find the path for your robot, even though one such thing exists. So if you take, what I'm saying is that if you take the union of CPs in which you compete for all possible rotations, and you take the union of all of them, at the end you may say that there's no path exists, but there may actually there may be a path. For example, for a certain orientation of a robot, you may not intersect with this union. So here, cases like that happens here, for example. Okay, if your robot is like this, okay, I mean it's going to intersect. If you do it, translate it like this, there's going to be intersection here. Okay, so if you take the union of all possible rotations, if you take the union of all these obstacles, you are going to find this, your robot is going to intersect with this, and there's no path exists. But a certain rotation, if you rotate your robot like here, and if it becomes horizontal, this orientation does not intersect with the obstacles. Now, so it means that we cannot take the conservative approach and take the union of all impossible places to say that this is the impossible places to go. So we need to somehow be able to move within this configuration space. And this is what we are going to propose. We are going to create ourselves slices of free spaces. For a certain orientation of the robot, for a fixed orientation of a robot, what we have is a certain free space. If you take the Minkowski sums, you get yourself a free space where the robot can move in this orientation. So for a theta I, we have a configuration space like this. If you change this theta to another angle, for example, if this was 150 degrees, for example, if theta I, you just make it 151 degrees. Okay, you make the rotation and you get yourself a different configuration space this time. Okay, and here each of these configurations are like slices. If you put all these on top of each other, you get a stack of configuration spaces. And what we do is to find a path for our robot, we make these translational rotations as separate actions. For example, within this configuration space, if we move from trapezoid to trapezoid within this configuration space, it means that we just do translation, we don't rotate our robot, and we are free to move to a certain place. For example, we move here, here, we come here, and we see that we are intersecting. There is no place to move more. But then maybe after we make a rotation, and it moves us to a place which is free in the other slice. Okay, a rotation may move you to a free location. So here we are going to generate 300. The bad thing is these rotations. How many slices you are going to have in your stack? You need to have again some discretization. Is it 1 degree, 1 degree, 1 degree? And the bad thing is that this solution does not guarantee a solution. If there exists one, you may miss a certain angle which is required to pass through because of your discretization. I mean, you can solve this by increasing your resolution. You can, instead of 360 slices, do 3,600 slices. It's going to increase your chance of finding a solution. But I mean, this is just a heuristic, which may not be robust. But in these cases, I mean, 1 degree is enough. I mean, it's very high resolution actually. 1 degree rotation probably is going to find you a solution anyway. So what we do is this. We compute the roadmap for each individual slide just as we did for just translational robots. And then for 2 neighboring slices, for theta I and theta I plus 1, what we do is we compute the intersection of a CP here with, not intersection, sorry, we intersect the trapezoids actually. And if for each intersection point of these trapezoids, we compute their intersection and we add nodes at this. So for example, we have a trapezoid here like this, which you can move. Okay, and there's another trapezoid like this, which may look different. Okay, so this trapezoid may be slightly different. So we intersect these 2, and for any point in the intersection, we say that you can move from this trapezoid to this. So by looking at these consecutive slices, we can see by a rotation which trapezoid we can move. I mean, we can only move to the trapezoids that are overlapping. Either they are not going to be the same trapezoids because the obstacles they have different shapes, but they are going to actually represent the same cell with slightly different shape. And our finding a path will be to find the path through these slices and within slices. So the algorithm becomes more complicated, but this is just an idea about a solution, how you can solve rotational robots. Okay, so that concludes our discussion about robot motion planning. Let me emphasize you again, in this path planning, we didn't even consider the case of finding the shortest path. So we just find a path, an arbitrary path that is going to take us from V start to V goal. And next week we are going to see how we can find shortest paths, which is going to take us from start to goal. So if you don't have any questions, I'm going to stop here. What is the deadline of your homework? It's this month? Yeah, 30th, so you still have a week. Yeah, you exactly have 1 week to work on the homework. And I'm going to give one last homework after this. So it's going to be a written homework, okay? Just before the finals. It's going to be an easy homework, okay? Now it's going to be a written homework about the visibility graphs and motion planning probably.